cos nx sin x and are all ordered. So what I mean by this, n not equal to m and for any n and m between signs and functions. Okay, so now let's do this very simple. And the interval is 0 to 2 pi, because beyond that the entire screen is not moving. Just 1 minute, please. So what I mean by that is integral 0 to 2 pi and nx is equal to 0. So this you can show is simply, for example, and what you have is this is equal to 1 upon n into 2 pi times 0. So this is equal to 0. Okay, and similarly we have the following. Similarly, when I look at the cosine function,
Hello.
Equal to
Hello.
hello.
Sir. Sir, ನಿಮ್ದು ನೆಟ್ವರ್ಕ್ ಡ್ರಾಪ್ ಆಗ್ತಾ ಇದ್ದಂಗಿದೆ ಸರ್.
ಹಲೋ. ನಾನೇನ್ ಮಾಡ್ಬೇಕು
ಸರ್? ಹಾ ಅದೇ.
ಯಾ.
ಫ್ರೀಸ್ ಆಗಿ ಬರ್ತಾ ಇದೆ ಸರ್.
Because so it's very difficult for me to do anything, you know.
Okay, sir. Okay, sir. No problem.
So thanks for pointing it out, but I can't help it.
Okay, sir. No problem. Okay.
Okay, so this is minus 1 upon n. Go next. Green. So by 1 upon n. So you said cosine is orthogonal to 1 for any value of n. Okay, now let's see. I use the cosine x plus cosine n minus m x. That's because this one is cosine nx cosine m rather cosine nx, cosine mx plus sine nx, sine mx. So this has to be divided by 2. Okay. So what we have from here is that, so I can write that integral as integral 0 to sine n mx half of integral 0 to sine n minus mx dx. So what from here is equal to 0 because n plus m is also an integer which is k, and I have already shown that cosine of any integer times x integrated between 0 and 2 pi. So here I have to look at n. What if anything? Then integral 0 dx or equal to 1/2 of integral 0 to 2 pi dx is equal to okay. So today it's a bit lousy. Okay, so when n equal to when n not equal to m, and hence it's integral. So what I have now is that integral 0 to 2 pi nx plus m. Okay, let us see what happens. Today everything is slow. So integral 0 to 2 pi sine nx sine mx dx is actually integral 0 to cosine n minus x dx minus of integral 0 to pi cosine n plus m x dx. Now this is 0 that we have already seen because n plus m is an integer. Now this 1/2 integral 0 to 2 pi cosine n minus x is only when you m integral survives, otherwise it will not survive. And so it just not. Now okay, integral 0 to 2 pi sine nx plus mx dx is equal to 1/2 of integral sine n dx 1/2 of integral 0 to 2 pi sine of n minus mx dx. Once again, sine x is sine n minus mx sine mx and d this is equal to all n and m. Let me move the thing. So that is because sine 0 is sine n. What I've shown here is that the constant one sine nx and cosine x form an orthonormal set over the then this actually I can write it as integral minus pi to pi, because one full cycle is what is for periodic. Okay, so I can have minus pi to pi instead of 0 to 2 pi. Sometimes I use it as 0 to 2 pi, sometimes I use it as what I can to integrate if it is periodic with periodicity 2 pi, that is f of x plus 2 pi is equal to f of x. Then s division minus pi or 0 to pi we want of in terms of constant cosine nx and sine nx. So to write it, what I am saying is f of x is equal to, let me call the constant term coefficient as a naught by 2, and then I can say sigma over n an cosine nx plus sigma over n b sin x. Now that I found out what this coefficient a naught is quite simple. It is exactly the way we did for orthogonal polynomials or for vector spaces. Is no different. It's exactly the same algebra. So if I take, say, for example, integral 0 dx integral 0 to pi dx plus sigma over n integral 0 to pi cosine nx dx plus sigma over n bn integral 0 to 2 pi sine nx dx, right? Because all I have done is integrated both the left hand and the right hand sides from 0 to 2 pi and have equated them. And I'm assuming that the integrals exist in all these cases. Okay, so if that is the case, you see that this goes to 0 because next orthogonal to the constant. Similarly, sin nx is orthogonal to the constant, so this goes to 0. And what I would get is equal to a naught by 2 into pi. Or is it a naught by 1 by pi integral 0 to 2 pi fx. So now we want to evaluate what happens. A and B and the whole thing by kx. cosine kx dx equal to 2 pi cosine kx dx plus sigma over n an integral 0 to 2 pi cosine nx cosine kx dx plus sigma over n bn integral 0 to sine x cosine kx. So what we have known is that cosine kx is orthogonal to constant, so this goes to 0, and this also goes to 0 because sine kx and cosine kx are orthogonal, and this gives me sigma over n an times pi into delta a or a pi, or again is equal to pi integral 0 to pi of x dx. If I want to get pk, function f of x by sine kx, and I will get a 0 by a plus sigma y integral 0 to 2 pi is a of x dx plus sigma over n bn integral 0 to 2 pi sine nx sine and cosine are orthogonal, and the last term is going to give me sigma over n pi integral 0 to 2 pi f of x. Here I made a mistake in the previous one. Range probably. So this I will write as fx cosine kx dx. Important. So I will refer to the so any periodic function can be expanded as a naught plus a cosine dx plus sigma over n sine n dx. So basically, this thing undergraduate algebra, very simple to get the coefficients. So I showed you that a naught is equal to 1 by pi integral 0 to 2 pi f1 upon pi integral 0 to 2 pi sine n dx and nx dx. Okay. Any questions so far? A very simple expansion of a periodic function between 0 and 2 pi in terms of cosine functions and sine functions with integer times the argument of the function. Any questions?
No, sir.
So I'll proceed. So now, simple example. Let me expand. Let's say x squared. So let me take the So I got this. Okay. So look at the following. Okay. I have minus pi here and plus pi here. And f of x in this region. What shape of the curve is it? Are you hearing me? What is the shape of the curve f of x equal to x squared? I will not proceed unless you answer yes or no. Do you know it?
Parabola, sir.
Why does it take you so long to actually say?
Sir, your voice is breaking.
Okay. So now what does it say? This is okay, similarly, I can have minus 2 pi minus 3 pi minus 4 pi minus 5. So you see that the function periodically extended over the entire range. Now I want to find out the coefficients. So how do I find out? Let me see. A0 by 2 is equal to 1 over integral minus pi to pi. I'll take minus pi to pi. F of x is x squared times here. Okay. So what does it mean? This gives me 1 into x cubed by 3 minus pi to plus pi. That's equal to 1 upon pi or 1 upon 3 pi if you want times pi cubed minus minus pi cubed is equal to 3 pi equal to 2 by 3 pi square. So now term which is a. I want to get equations for an and bn. So let me see. Let me get. So what is an equal to 1 upon pi integral minus pi to pi x squared cosine nx. Okay. Now I do something which is trivial. What kind of a function is x squared over the integral minus pi to pi? The value of x squared changing x to minus x. If I take fx equal to x squared and f minus x is also x squared, so x squared is an even function. Cosine is a function cosine of minus theta. So what we have is this I can actually write it as 2 by pi integral 0 to pi x squared and x. No, I will get box. Whenever you have something, some function multiplied by x to the power n, you keep integrating by part to reduce the power of n in the integral. Okay, you want x to the power n should become x to the n minus 1, etc. And finally a constant so that it is easy to integrate out the remaining part. So how does one do it? So I'll treat this one as u and this as b pi. So what is b? B is integral of cosine n. Integral cosine n x 1 upon n sin n x. 2b, which is x squared times I have cosine n x is integrated x divided by between minus pi and pi. Okay, and then I have minus of 2 upon n because when I differentiate cosine, I've already integrated, it gives me 1 upon n sin x. So this will give me 2 upon pi. Integral 0 to pi. I have x sin x. Sin nx dx. Sine of 0 is 0. Okay, and so I can forget the first term. And the second 2 divided by pi is on the outside side. Okay. X, I have to integrate sin x and differentiate x. So if I integrate sin x, I get cos nx minus n, right? And times x, okay, this is 0.5, right? Because it is u. Okay, so this is a u times integrate of this is v and this minus cos nx by n. So I'll get that minus I have 1 upon n minus 2 upon n squared by NX dx. Okay, so what do you get from this term? Let me print it out. What do you get from this term? Because integral 0 by sin NX dx should be 0, right? So because this goes to 0, and this will this will be equal to minus 4 by n squared into 1 upon pi into cosine nx x between 0 and pi. Okay. There is no two there, so there should be no two there. Anyway, I mean you can check it out afterwards. Okay. So this is going to give me 2 square. Okay, and this one this will be 1 upon pi into this will give me 0 1 next to pi. So I'll have so this is okay. Pi.
So
cosine
negative and negative will be
n.
positive.
No, negative won't be positive. Negative won't be positive because I have taken the correct sign. What this I can actually write it as minus 1 to the power n. Just a minute. I think maybe you are right because anything but 1 should be minus. You are right. So this is minus 1 to the power n 4 by n squared n greater than 0. Okay. So this value of a equal to minus 1 to the power n 4 on n squared. Right. Now let us see what happens to Pn. I can write on it as equal to integral 0 to sorry, I have sin nx times x squared dx. Okay. Now, what is the nature of the function square? It is a function. So, what is sin nx?
The root function.
Argument x to minus x, whatever to sin nx, it changes sign, right? So this is an odd function because sin nx is equal to minus of sin minus nx. Okay. So because of that, Bn is equal to 0. What about the even function? Yeah, yeah. I hope you're hearing me. So tell what answer is. What kind of function will you function? What kind of a function is even function into even function?
Sir, even function into even function is even function.
Odd function into even function?
Odd function.
So if you integrate an odd function over a symmetric interval about 0, what happens to the integral?
0, sir.
0, because in one part of the integration, if the negative integral on the positive side, it will give a positive integral, so the two will cancel because the two are equal. So Bn equal to 0 for all n as x squared is an even function. 2/3 pi squared plus minus sigma over n minus and cosine nx is even. So only even functions will give you the contribution. Odd function won't give you the contribution. And of course, the constant is always an even function. So you will have that equal to the constant time equal to 2 by 3 pi r square, pi square rather. Okay. So this is something that I've just example expand a Fourier series, a periodic function, a Fourier series. It can be any periodic. Okay, does not matter. Now, Fourier series in general. Size continuous functions. In the intro, minus 25. For example, let me take the following piecewise. So I have 0 minus pi plus pi. So it can go, it is negative like that, 0 region. 0 just stays positive. Then of course, it might come down to 0 and continue. This is a different function. In solid state physics, it's called chronic. You have periodic boxes. Okay, so you can look at these as periodic boxes. You can write them. This is one box. This is another box. So there is an action around that. You have a negative potential, and in the issues you can take it as potential. So that the negative constant is is a box, and then you have a zero potential, and then again the box, and so forth. So it is what's called usually a model that is used in any model for eligibility. Okay. I'm just telling you that why this thing is important. Now, in this, now we can find the function which is f of x less than x less than 0, f of x equal to 1. Let me take the constant to be 1 for this thing 0 less than x less than 1. Okay, so now the question is what's x? So discontinuity is interesting. The split series can be summed at the discontinuity. So what happens is like this. So if I have a discontinuity of this kind, okay, then initiate Fourier series goes as so, which means that cutting is equal to one of the discontinuity and fixed equal to particular value. And for n, what we'll have is a slightly different one. So let me try to change the color. Partial sums. Okay, it is some oscillates about the constant value and pass through the average of the jump. So once again, let the screen move. Screen. Oh. See here, the jump is at minus pi, 0 and pi, right? So, for example, the jump at minus pi, if you look at, you have at minus pi, the value will be value of the summation. Actually, you some amount of time because it is 1/2 of f of minus pi minus f plus of plus epsilon is a basic value around. So this is minus pi. So this is minus pi minus epsilon. This is minus pi plus epsilon. So you see that it becomes the average. And so you can actually sum it at different wherever you are. there is an undershoot before and after. Let me see. Okay, after the discontinuity, it show up. Means if we have something going like this, okay, so it shows a slight dip here, goes the overshoot and under. Okay, so this is under. So this is called a Gibbs phenomenon in this thing, summing of the. Okay, so that is the way to sum the series. It is discussion by Fedger summation. Let me illustrate what is Fedger summation. Okay, see, all of you must have done binomial theorem, right? Example of Fedger summation. So all of you have done the binomial theorem. Minus 1 is that is 1 upon 1 plus x to the minus 1 is 1 upon 1 plus x. This is equal to 1 minus x plus x squared minus x cubed plus x to the power 4 minus x to the power 5, etc., etc., etc. So for x equal to 1, okay, left hand side is equal to 1/2. But what was right? Whether you stop after an even number of terms or an odd number of terms, what you are going to get is either 0 or 1. If you stop at even number of terms, you get 0. If you stop at odd number of terms, you get 1. So what I can actually do in this case is take the summation partial and define partial sum, which is S1 is just the term. S2 is equal to 1, that is equal to 0. S3 is equal to at x equal to 0, it is 1 minus 1 plus 1 is equal to 1. S4 is equal to 0 and so on and so forth. Okay. So now let's so I'll say that the summation S is equal to n sigma over n Sn. Okay, when you do this, what do you get? Okay, so if I take this one, S2 will be 1 plus 0 by 2 equal to 1/2 because you have two terms. The first term is 1, the second term is 0, it is 1/2. And S3 what is the S3? Once if the screen moves, I'll tell you what it is. So the value of is equal to 1 plus 0 plus 1 is equal to 2/3. Let me see whether it's right. So I did right finally. It's as clear as myself. Can't help it. Okay. And S4 will be 4/4. S equal to 3/5. S6 is equal to half. So you'll see that slowly everything is going to converge to, because S7 will be 4/7. Okay, so it starts approaching 1/2 very slowly. So this is the special summability. So this gives me the value of 1 minus x that's equal to 1 as discontinuities you have to carry out a special summation. But anyway, I mean that is not right now very important. But I just wanted to tell you. Okay. Let me see whether I can do what. Oh. My screen is confusing. Yeah. Now, so far we were discussing functions with periodicity 2π. That is when functions have arbitrary period. That means I take a function f of x plus t is equal to f of x. So this is arbitrary periodicity. Like what you think using, because unit constants are need not be too technical. So you will have periodicity of potential. And similarly, here periodicity of function is t. Okay. Now in this case, can we carry out this Fourier series expansion of such functions? The point is replace the variable by t is equal to 2π. Then what happens is the following. That is, if you take f of t, okay, then what you will find is f of t will have a periodicity of 2π. Plus take x to x plus t, capital T is not t So it goes to 2 pi by t into plus t is equal to 2 pi x by t plus 2 pi, or that's equal to t plus 2 pi. So translating x by the quantity t is the same as translating t, small t, by a quantity 2 pi. So all you need to do is change the variable from x to t equal to 2 pi x by capital T, which is the periodicity of the function f of x. Is this clear? This is something that is routinely done in solid state science. Okay, we will come to that probably when you study things like energy band theory or lattice vibrations and so forth. Okay, so is this point clear? Hello, is this clear?
Sir, how x dash is equal to x plus t?
What is it?
How x dash is equal to x plus t?
Because I have the following, I take x dash equal to x plus t. Okay, then showing here. So which means that if f of x plus capital T is equal to f of x, it's just a matter of scaling the variables. So instead of having a periodicity t, you call the periodicity t to be 2 pi. Okay, if you say that t is equal to 2 pi, then you are scaling the variable from x to t equal to 2 pi x by t, because x is going from 0 to 2 pi. Is this point clear?
Yes, sir.
Okay, so let me proceed. So if this is the case, then what we can do is we can read A and A, A, okay, so pi is t or pi replaced by 2. Yeah, okay, ಕಳಿಸ್ತೀನಿ. Okay, okay. After 12 o'clock ಕಳಿಸ್ತೀನಿ. Okay. Okay, thank you. Bye. Okay, so what we had was A0 was equal to 1 upon pi integral 0 to 1 f of x dx, right? So what happens is the periodicity is not 2 pi, periodicity is t. So because of that, pi will become 2 by t, and 2 pi will become t. 1 by pi will become 2 by t. Okay, so it will be equal to 0 to t f of x dx. Similarly, a n by will also be equal to 1 upon pi integral 0 to 2 pi f of x sine nx dx. T is equal to t integral 0 to t f of x sine nx dx. I can always shift my integration to, I can say that instead of integral 0 to t and integral s by 2, just integral 0 by integral minus 5. So I will replace it. There is a problem. And some in the region where it says L equal to T. Okay. So sometimes, but I will not use that. I will always use the full periodicity as T, not half periodicity as L. Okay. So that is why I will always use minus T by 2 plus T by 2 or integral 0 to T. Okay. So if you do that, you get the T function f of x as a naught by 2 plus n by 1 to infinity a n cosine nx plus sigma over n equal to actually I can this goes over to f t where t is equal to 2 by x by capital T scale variable. So this will become plus sigma n is equal to 1 a n cosine n t plus sigma over n is equal to 1 to infinity b n sine of n. So this is for 0 to 2 pi and this will be for 0 to t. Okay, so whenever I have a periodicity 0 to t, I change my variables to n pi x by t, capital T, n pi x by capital T, and then I have this one. So this is in general the Fourier series that is used for any arbitrary period t. Any questions so far? Just a change of variables. Any questions?
No, sir.
Okay, so now let me go to slightly different. One second. So now when you have these expansions, of some arbitrary. Let me see whether I write everything that I've written. Yeah, okay. Then, for example, let us say that f of x is equal to 1 for x belonging to the interval 0 to pi. And so I've just given this function over a narrow interval. Okay. So this is this value x 0 pi. I want to find it in a Fourier series. So what can I do? I can periodically for the entire space. Okay. So there I can repeat as so I have to just go and close the notes. Okay. Now I can expand it in many different ways. Okay. So let me see which are the ways in which I can expand it in the following way. Say this time, so I can write that way. Let me wait if it. Okay, so let me see. Okay, so I can do by so if you just for example, by okay, so we will see is that between minus pi and pi, the function is even. F of x has been expanded, has been extended rather, in an even fashion. So if I were to expand f of x, then I only have a sine series. Okay. Cosine function corresponds to the A will correspond to integration of function of x. It's not multiplied by x and but I can I can also expand it in a slightly different fashion, which is this one. 0 pi. Okay, I can expand it such that it just extends beyond this. This is pi, and then this is 2 pi, 3 pi, and I can go on like that. So the way I have expanded it, this f of x, the entire is function. Okay, so I can have fx expanded in this fashion. This is equal to sigma over n bn sin nx. Okay, what I am interested is in only the value in this region. I'm only interested in this region, the expansion. But because I want to extend it periodically and use the Fourier series, I will take this t to be 0 to pi and then extend it to 2 pi or minus pi and so forth in different fashions. In this way of expanding it, I'm going to get an odd function over the entire interval, and this way of extending it here is an even function. So I can get a function f of x expanded only in cosine terms or only in sine terms. And I can also expand it differently. There's one more way in which I can expand it. For example, I can take this is 0, then I just take it as here, and then this pi, okay, and then I have a about it because this is the problem of the online is terrible on computers. So then very yeah, so I'll have can have this way. Okay, so neither odd neither odd not even. Yeah. So in the next stage, we want the following: f of x would be a naught by 2 because it is neither periodic, neither even function or odd function. Both the cosine sine terms. So you have 1 plus sigma n sin x. Let me see. Try that again. Okay, so what we have is given a function for by or that you want to then we can so resulting Fourier series is either only involves functions or only functions. Or both. So this is a name. The name is the first two expansions are called half-range expansions. Means only using sign functions to expand, only sign functions to expand. So the Fourier series is called half-range expansions. And then you have a full cosine expansion of the function. The third case is called a full range expansion. I'm just telling you that when you expand functions, it's not necessary that the function should find kind of 0 to 0. Maybe only find out part of the interval, and if you only get only a series, the function has that interval, you can extend the function either even function. If you want only a sine, you can expand only the sine function, or extend it to as an odd function, or if you want both sine and cosine, then you can extend the function in any arbitrary fashion. Okay. Things that is used in Fourier series, which is half-range expansions and full-range expansion. So basically, what we have for the Fourier series, an expansion of a periodicity t as of x is equal to a naught by 2 plus now, you see, I can write down. You remember the Euler's formula for cosine and sine functions? You have what is e to the power I theta sine theta? What equal to? Reverse theta. Okay. So, write down cos theta as equal to e to the power I theta plus e minus I theta. And sine theta I can write as 1 upon 2i, okay, cos theta minus, rather e to the minus, okay, 1 upon 2i for I theta minus of e to the minus I theta. So I can support. That's the for the of s of s equal to a naught by 2 plus n n for I n pi phi t plus b to the minus I n pi phi t plus sigma over n Bn upon 2I into e to the power I n pi x by t minus e to the minus I n pi x. So all I did was for cosine. Now what I can do is the following. Are you able to see the screen now? Hello?
Sir.
Okay, I think my internet went on a blink. So I can actually write that is equal to a naught by 2 plus sigma over n an by 2 plus bn by 2I, okay, into e to the I n pi x by t plus sigma over n an by 2, just a minute, am I doing it the right thing? An plus an by 2 minus bn by 2I times e to the minus I n pi x by t, right? So I call Cn as equal to an by 2 plus b by 2I and Cn star as equal to an by 2 minus bn by 2I. It's just simple algebra, okay? So that I have f of x is equal to a naught by 2 plus sigma over n Cn e to the I n pi x by t plus sigma over n Cn star e to the minus I n pi x by t, or I can just write it as f of x is equal to some sigma over n equal to minus infinity to plus infinity dn e to the t, where dn is equal to Cn for n greater than 0 and dn equal to Cn star for n less than 0 and dn equal to a naught by 2 for n equal to 0. So you see how I can get a complex Fourier series starting with just the sine and cosine expansions and using Euler's formula for e to the power I theta. Okay, so how one can actually get a complex Fourier series, and this complex Fourier series is what you use extensively in solid state physics, because you have the periodicity over the entire lattice and you want to expand potentials which are periodic, or you want to expand the other properties which are periodic in terms of Fourier series, and it makes it much simpler to solve the problem, okay, because it exploits the translational symmetry of the lattice. Okay, so what I'm going to do is, today I'm going to stop here because very unhappy with the way the internet is behaving. But anyway, I only have about 2 minutes left of the actual time. So I'll stop at this and I will continue from here in the Wednesday's class, and I'll go over to what are called Fourier transforms, because they are some things that people use extensively in many applications. Okay, so let me stop at this point, and I can stop sharing. If you have any questions, please ask me now. Any questions?
No, sir.
So we can stop then. Okay, so I'm going to stop and we'll continue again on Wednesday. Okay, thank you.